মধ্যে কুমিল্লা ভিক্টোরিয়ান্স দলে ফিরিয়েছে ফাফ ডুপ্লেসি ও সুনীল নারায়ণের মতো তারকা ক্রিকেটারদের। এছাড়াও গুঞ্জন
Remember last time we have learned the squeeze theorem. Squeeze theorem. We have theorem D. We have three functions f, g, and h. Classifying the following equalities: fx less than or equal to gx, gx is less than or equal to hx. For Rx near C, except possibly at C. If we have, this means if we have here fx approaches L as x is near C, hx approaches L, same thing we have this function gx also approaches L. Okay, this is the squeeze theorem. Okay. For example, we will use squeeze theorem to calculate to assimilate we have brought. So calculate this. As remember, we have made this equality, this limit. This limit before we have made it. We have touched this one before. Limit is 1. How we get this result? We just choose some points, and then we find the sin x or x, the values of sin x or x, and we get the limit is 1. And now we will prove it. Before we prove it, first we should have a conclusion is 1 minus x squared over 6 less than sin x or x less than 1. For x is near but different from 0. This means this inequality succeeds. What can we conclude about this limit? Here, we will choose fx. Fx is 1 minus x squared over 6. And choose gx is equal to sin x or x. And hx is 1. And we know the equalities is fx is less than or equal to gx, less than or equal to hx. Now we just write Vx is near 1. X is near 1. We know x is near 0 here. X is near 0. We know fx is 1 minus x squared over 6. So we have fx is near 1. And hx, because this is a constant fraction, so it's always near 1. This means Vx is near 0. We have fx is near 1, hx is near 1. And so by the squeeze theorem, we have this is a middle function. It's also near 1. So by theorem D, we have this limit is 1. This is how this will teach us, this will tell us how to use the squeeze theorem. It's very important to find the proper fx and hx. Okay, and the theorem B we learned it before is about the limits of polynomial functions. This means can always be found by substitution, and limits of rational functions can be found by substitution as long as the denominator is not there at the limit point. This substitution though applies to the trigonometric functions as well. This result is stated next. This means we will learn limits involving trigonometric functions. We have theorem A, the limits of trigonometric functions for every real number C in the functions domain. We have this sin t trigonometric function. T approaches C of sin t is sin C. T approaches C of cosine t is cosine C. So it's the same tan t, second t, cosine t, cosecant t. We can use the substitution. For example, we find example 1 here. Example 1 here. We find that this is example 1. We find this limit, right? Is limit. Right, this is limit. Here is t approaches 0, t square cosine t over t plus 1. We can use the substitution because the denominator is not 0 at the limit point 0. So when t approaches 0, t square is t plus 1 approaches 1. And t approaches 0, t square approaches 0. This is by substitution, this is cosine 0. When a cosine 0 is 1, so 0 times 1 over 1. So it's 0. So the limit is 0. Okay? And now we will learn very special trigonometric limits. They are very important. The first one is limit. T approaches 0, sin t over t. This is 1. And the second one is limit t approaches 0, 1 minus cosine t over t. This one is 0. This one, the first one, we put by the squeeze theorem. And the second one, maybe we can put after we learned the air L'Hopital's law. L'Hopital's, this means in Chinese is 罗必达法则. We will put the second one. And here we should remember these results. Okay, and also we will use these two input limits. We will apply these input limits to solve A, B, C. Okay, the two input limits. First one is this one right here to remind you. Second one is this one. There. And we will solve A. So A, find its limit. Here, we can find this limit x approaches 0, sin 3x over x, right? We can say we will use the first important limit, but it's different from 1, right? This is sin t, this is t. But here is sin 3x, x. So if I write like this limit x approaches 0, I write this sin 3x, I write, well, this is t, this is t, this is t. So I just write the 3x. Of course, they are not the same. So I should times 3. Okay? And we have like the properties. We know how to calculate the limit. We have theorem, maybe this is theorem what? Theorem A, I forgot. Now, from this, we know this is 3 times x approaches 0, sin 3x over 3x. And here, we can write like this. We write 3x is t. We know x approaches 0. We can find this means t approaches 0, right? X approaches 0, 3x approaches 0. So we can write this 3 times the limit. This is t approaches x approaches 0, means t approaches 0. The sin 3x is sin t. 3x is t. So we find by the first important limit, we find it is 3 times 1. So this is 3, right? This is A. Hello, and a question for A? And a question for A? No. How about the other students? And a question for A? No? Okay, now we continue. B, number B. Here, B we write, we want to find the limit. T approaches 0, 1 minus cosine t over sin t, right? Okay, we say it's different from 1. It's also different from the second one, the first one, the second, they are not the same. But here we can find this is 1 minus cosine t. Here is also 1 minus cosine t. This is sin t. This is also, we have sin t here, right? So maybe you will write like this. This is very flexible. In Chinese, this is, you know this word? Maybe I write here. This word, this Chinese word. Yeah, 灵活的. So we are here is t. This means we haven't t. So I just add a t. Write a t here, right? Okay. I divide the t. This means I should time t, right? In case they are the same. Here they are the same, right? So I write this limit. T approaches 0, 1 minus cosine t over t times limit t approaches 0, the t over sin t. Maybe I can write this 1 over sin t over t. Okay? So here we know this limit, the first one is the second important limit, we find it is 0. And the second one, we can write is 1 over limit t approaches 0, sin t over t. So we can find is 0 times 1 is 0. So the data is 0. Second one, and question. Do you understand them? And question second one, B, and question for B. This means no question. Understand, right? Okay, maybe for C, have a try. For C, answer. C, answer. Try. Flexible is a Chinese word link for that. In English is Flexibale. Oh, BLE. Flexibale. Flexible. Flexible. Okay, sunrise around Thailand. Okay. Can write 3x, 3x is, no, you can write you write x is 3x, no, you can't write like this because this will be confused. 3 is x is 3x, no, you can't write like this. This one. Now, do you want me to explain it? Exam C? Okay, please listen to me carefully. Exam C. See, here we write the sum for x. We know the important limit is this one. This is x or x. This is x, x, x. Oh, you write the variable is t, it's the same, but the limit is 1, right? And here is 4x, and maybe you can write like this. This is sin 4x. Okay, this is over tiny x. Tiny x we know is sin x over cos x, right? So we write is equal to limit x approaches 0 is sin 4x over cos x times over sin x over sin x times cos x. Okay, and by the substitution, we know we can write this limit x approaches 0 sin 4x over sin x times limit x approaches 0 cos x, right? You know, when x approaches 0, here, this one. Cos x approaches cos 0, x approaches 0. Cos 0 is 1, right? So the right is limit x approaches 0, sin 4x over sin x, right? Over sin x. And now, if we want to use this important limit, this is sin x. This should divide by x. So this is sin 4x. 4x, which the right is sin 4x divided by 4x, right? Same, and times 4x over sin x. Okay, and we can continue to write this limit x approaches 0, sin 4x over 4x times limit x approaches 0. This is 4. 4 is a constant. Maybe I write in the front. 4 is x over sin x. And then we know that this one, x approaches 0. So it's almost the same with sin 3x over 3x. So this is 1 times this is 4 times x over sin x. The limit is also 1. So this is 4. Right? Okay, and a question? No? No questions? Is that infinity? What is infinity? No, no infinity is infinite number. No question? Huh? Tiny x is the definition for tiny x. Is the definition for tiny x. I think we have learned in chapter 01. Maybe you can review chapter 01.
It is now 5 p.m.
Yeah. Chapter 01. We have introduced the tiny x, cotiny x, secant x, cosecant x. We have introduced this trigonometric fractions. Oh, I see a picture. Okay. Yes, it is right. Okay, it's right. Lily. Okay, now here, almost the same method. Okay, if no questions, if we will learn next, we will learn limits at infinity. This means when we write x approaches infinity, we are not implying that somewhere from far to the right on the x-axis there is a number bigger than all the other numbers that x is approaching. Okay, rather, we use x approaches infinity as a shorthand way of seeing that x gets larger and larger without bound. Okay, this means x gets larger and larger without bound. It not means x approaches a very big number. It's not like this. In the table in Fig 2, okay, we see Fig 2, we have listed values of this function, x over 1 plus x squared, for several values of x. That means x 10, 100, 1000. We can find it appears that gx is 0.099, 0.010, 0.001. When it appears that gx gets smaller and smaller as x gets larger and larger. So we write this is limit. This means x gets larger and larger without bound. X over 1 plus x squared is 0. Okay, we can experiment with negative numbers. So far, a number far to the left of 0 on the real number line would lead us to right. This is x approaching x with negative numbers. X approaches minus infinity. We can also find this limit is 0. Okay, this is the limit at infinity. Limits at infinity. Okay. We will give rigorous definitions of limits as x approaches. Here is positive infinity, negative infinity. Here, analog with our epsilon dash definition for ordinary limits. This means x approaches a constant c. This is a finite number. We make the following definition. The limit as x approaches infinity. We like to have b defined on c infinity for some number c. We see that this limit is L. If for each epsilon is greater than 0, there is a corresponding number I. Number I, such that because x gets larger and larger without bounds. So this means x greater than I implies the absolute value between fx and L is less than epsilon. Okay? We will note that m can and all usually does depend on epsilon in general. Smaller epsilon is, the larger m will have to be. The graph in Fig 3 will help you to understand what we are seeing. Now we have here, this is the curve of y is fx. And we know this means x is greater than m. Okay, here this is m. This is greater than. This means x like this. Greater than. You know, the absolute values are fx minus L less than epsilon. So from this, we know fx is between L minus epsilon and L plus epsilon. So here, if this is epsilon, this is L minus epsilon, L plus epsilon. This means, okay, Vx is greater than our fx is in this rate, right? This means in this rate, okay? And also we will give the definition as x approaches minus negative infinity. We will define f on minus infinity to c for some number c. We say that the limit is L. If for each epsilon is greater than 0, there is a corresponding number m, such that bx is less than m, implies that fx minus L. Then we take the epsilon values less than epsilon. Okay, less than epsilon. After we know the definition of limits at infinity, we will give you some examples. Example 1, this means example 2, want to prove that this limit is 0. And at the first, we just give some point. It appears that gx approaches 0. Here, example 2, we want to operate. Okay. Here, we should notice that x approaches infinity. Here, we use a standard trick. We should divide. This is very important. Divide the numerator. X is numerator. 1 plus x squared is the denominator. Divide the numerator and the denominator by the highest power of x that appears in the denominator. You know, the highest power of x, the highest power of x, the highest power of x of the numerator is x, the denominator is x squared. So the highest power of x is x squared. That appears in the denominator, that is x squared. Okay, we're right. Divided the numerator by x squared. Divided the denominator by x squared. So they are same, right? They all divided the same x squared. And then we find is equal to limit x approaches infinity, x over x squared is 1 over x. 1 plus x squared over x squared is equal to 1 over x squared plus 1, right? And we can write this limit x approaches infinity, 1 over x squared plus 1. It's the limit x approaches infinity, 1 over x, right? And then we write, here we see the numerator. X gets larger and larger without bound. X gets larger and larger without bound. 1 over x, this means gets smaller and smaller, approaches 0, right? And okay, so the numerator is 0. And also, x gets larger and larger without bound. 1 over x squared also gets smaller and smaller until approaches 0. So this is 0, this is a constant 1. So the denominator is not 0. So this means we write this is right. Okay, so we find that this is 0. So we find so that we just separate. This means this is 0. Okay, so we should use a standard. You should remember when we calculate the limit, this is x approaches infinity. We should divide numerator and the denominator by the highest power of x. Okay, the highest power of x. Questions? Example 2. Questions? What? The highest power of x, where is x squared? Zero? Do you know what's his meaning?
Can you hear me?
We should divide what?
Hello, ma'am. Can you hear me?
The
Hello.
the heaviest power of both x numerator and denominator.
Ma'am, can you hear me?
How to divide what? If you find the hence the power is x squared, just divide it by x squared. If you find the highest power is x squared, just divide the numerator and the denominator by x squared. What? What? Comments okay, of course. I just the example and question. Do you know what's the meaning? No? Okay, okay. Maybe give you more exercise to understand there. Okay? More exercise to understand there. Okay, for this one. Okay, hello students, have a try exam 3 by yourself and then we will explain exam 3. Yeah. Okay, we explain it. Okay. Now here we should know that this is also x approaches just the negative infinity is also limited at infinity, right? So we use a standard trick. Divided the numerator and the denominator by the highest power of x. This tells me the highest power of x is equal to the highest power is equal to, of course, x cubed, right? The highest power. So we divide the numerator by x cubed. Divide the denominator by x cubed, the highest power. Then we simplify it. We know here 2x cubed over x cubed is 2, right? And 1 plus x cubed over x cubed is 1 over x cubed plus 1. So we find the limit is 2 over limit x approaches infinity. Oh, this is minus infinity, negative infinity, 1 over x cubed. This is plus 1. And we know we just need to calculate this one. This means x approaches negative infinity, and we know x approaches negative infinity. This means the absolute values of x gets larger and larger, right? This means x is a very small negative number. This means x gets smaller and smaller. This is also negative, so we can find this is 0 limit, right? So limit, so it's 2 over 0 plus 1. This is 2. Find it. The answer is 2. Okay, any questions for this? Exam 3, understand? Understand? Okay. Any questions, exam 3? Okay, no. Here. We divide both the numerator and the denominator by x cubed. We find this is 2. And we will give you, this is a graph of f(x) is 2x cubed over 1 plus x cubed. We find that here, because the limit is 2, this means x approaches negative infinity. Here, negative infinity. Here, this is the line 2. The curve approaches 2. And we can also find this one. Limit is also 2. So we find x gets larger and larger without bound. Fx also approaches 2. So like this. And now I hope you can know how to find the limits at infinity. Now we will give you the limits of sequence like this. The domain for some fractions is the set of natural numbers 1, 2, 3, and so on. In this situation, we usually write an rather than an, like this, to denote the nth term of the sequence. Or we write like this, an, to denote the whole sequence. For example, we might define the sequence by right. An is equal to n over n plus 1. Okay, now n is 1, 2, 3, and so on. So we find Vn is 1, we have ny is 1 over 2. Vn is 2, so it's 2 over 3. And we find n is 3, A3 is equal to 3 over 4. And maybe you can find 100 is 100 over 101. It looks as if these values are approaching 1. We find this are approaching 1. So it seems reasonable to say for this sequence, the limit n approaches infinity, n over n plus 1 is 1. Okay. The next definition gives meaning to this idea of the limit of a sequence. Okay. So we give the definition that this limit of sequence is not a function. This is a special function, right? Let an be defined for all natural numbers greater than or equal to some number c. We say that this limit is L, this is sequence. N approaches infinity, and this is L. If is absolute greater than 0, here, now we know this is N approaches infinity. It's almost it's like X approaches infinity. So this means there is a corresponding natural number I, such that we know X approaches infinity. We know this X is greater than n. So here we write this n greater than n is greater than n, implies that the n, because an approaches L, so the absolute values of an minus L less than epsilon. So this is the definition of limit of a sequence. Okay. Notice that this definition is nearly identical to the definition of limits at infinity of a function. The only difference is that now we are requiring that the argument to the function be a natural number. So this means an is 1, 2, 3, 4, 5, 6, 7, 100, and so on. And we might expect the man limit theorem holds for a sequence. Sequence is the man limit theorem. This means an, this means the limit. We will write an. This is an plus or minus bn. This is the new sequence. We find the limit. So we can write this as the limit n approaches infinity is equal to a plus or minus b, and so on. We have many man limit theorem results. Okay. Here, this one. Well, this one, we can find this is the limit. Example 1 and example 4. This is n plus 1 over n plus 2. We can write by the man limit theorem, this is n plus 1 over n plus 2. Here we write the power is 1 over 2. And we can also write is equal, we first find the limit, then this n plus 1, n plus 2, and then this is 1 over 2. We use man limit theorem. Okay, now, so our target is to find this one. This one. Okay, guys? And guys, it's approach. Okay, guys? Why? You know? Why? Maybe you should figure out this one. Do you know how to calculate this one? This is just the same as example 3, example 2. Both divided the numerator and the denominator by the highest power of x, right? So the highest power of x is x, right? So divided by x. One plus x or 1 over x. 1 plus 2 over x. You find this is x approaching infinity. This is 1 plus 0, 1 plus 0. So this is 1, right? And when we write when we find the limit of sequence like this, we will also use a standard trick. This means find the highest power of n, not x. So this is yes. Given the n approaches infinity, n plus 1 over n plus 2 over n. 1 plus 1 over n, 1 plus 2 over n. So it's 1 plus 0, 1 plus 0 is 1. Same method. Same method. Okay. Any problems, any questions? For example, 4. Any questions? This means no. Okay. Now say this is the graph. A is 5, A is 10, A is 15, A is 30, 20. We can find it's near 1. Okay. Okay. And now we will learn this limits at infinity. Now we will learn this infinite limits. This means when consider the function, right? 1 over x minus 2, which is graphed in figure 6. See, there's figure 6. Like this. We know x as x gets close to 2 from the left. This is 2. Close to from the left, this means x is close to 2 from left. We find fx approaches what? Fx approaches negative infinity, right? Approaches negative infinity. Seems to decrease without bound. Decrease without bound. Similarly, as x approaches 2 from right. Okay, x like this. This is fx, when the function seems to increase without bound. It therefore makes no sense to talk about x approaches 2, but we think it's reasonable to write because x approaches 2 from left. We know this approaches negative infinity, decrease without bound. So we write like this: it's negative infinity, and this x approaches 2 from right. X over 2 is increase without bound. So write it. Infinity. Okay, right, it's infinity. So this means infinite limits. Infinite limits. And here is the precise definition. We say x approaches c from right, fx is infinity if for every positive number n there is a corresponding depth greater than 0 such that because x approaches c from right, this means x is greater than c. This means x minus c less than depth greater than 0 implies, here this means fx gets larger and larger without bound. So this means fx can be greater than any positive number n. This means fx gets greater, larger and larger without bound. Okay. In other words, fx can be made as large as we wish. Okay. Greater than any m that we choose by taking x to be sufficiently close to, but not to the right of c. Here are corresponding definitions. So here this means positive infinity. So that's negative infinity from c from left. Infinity opposite c from left. Negative infinity Also, x approaches infinity, the limit infinity. Approaches infinity, limit negative infinity. Approaches negative infinity, limit infinity. Approaches minus infinity, fx approaches minus infinity. Okay, this means we should know the infinite limit. Okay, we will meet. Then exam 6, we will see exam 6 together. Okay, exam 6 here, which is different from x approaches infinity. We should notice that this is approach 2 from right. Okay, and the numerator is x plus 2, x plus 1. And the denominator, we will factor. Factor is 3, right? X minus 2, x minus 2. And if we use man-limit theorem, if we write like this, we find this wrong. Here is x plus 1 over the 0 times minus 1, right? So this is division by 0. So we counteract like this. Okay, we counteract like this. But how to find this limit? We just analyze it. We can find this here. We know x approaches 2 from the right. The numerator approaches 3. We are sure, right? X approaches 3. And we know x minus 3 approaches minus 1, right? And we know x approaches 2 approaches, this means approaches 0 from the right. This means x minus 2 greater than 0. And thus we know the numerator approaches 3. The denominator approaches, this is positive. We know this is positive. This is x minus 2 greater than 0. And this is negative. This is positive. So this means approaches. This means this is negative, right? We can analyze negative. Thus, the numerator is approaching 3, but the denominator is negative and approaching 0. You know, we can find the numerator approaches 3. The numerator is negative. It's approaching 0. Okay, guys, this approaching what? Maybe I give you an example. We can think of numerator approaches 0. Next, numerator approaches 0, approaching 3. Denominator is approaching 0. It's negative, right? For example, if we use 3 over this is this number, if this number, yes, it's infinity is positive or negative. Positive or negative? This one is positive or negative? Negative. So this means we just, this is not right. We just think of like this to help us understand it, right? So we just write is negative infinity, right? Okay, but you can't, in your examination, you can't write this 3 over this 1. This is wrong. Okay, you can't write it like this. We just analyze like this, help us to understand it. So we find this. We conclude that is negative infinity. Exam 6 and questions No? Hello, students online and questions. No. How about the other students? Any questions? Okay, maybe we should have a little break. Have a break for a while. Okay, have a break. Okay, have a break. Have a rest for a while, and then we will learn the relation to asymptotes. Okay, hello. Let's come back to our class. Okay, and now we will learn the relation to asymptotes. Asymptotes were discussed briefly in section 0.5, but now we can see more about them. The line X is C right here. Axis C is a vertical asymptote of the graph of other y-axis if any of the following four statements is true. Okay, this is a vertical asymptote. If this limit from right, this means the one-sided limits. This is infinity, negative infinity, infinity, or negative infinity. And we will see axis C is a vertical asymptote. Okay, now axis C, right finger 6. Finger 6, we know finger 6. Oh, here, finger 6, we find this X approaches C from the left, so this is negative infinity, infinity, 4. One of them 16, and we see here, this is X is 2. This is a vertical line. And from the finger 6, we know the curve or the graph of fx is approaching 2, right? Like this. They are almost is approaching this curve, right? So when we call this x2 is a vertical asymptote. Okay, asymptote. Like this. And likewise, the lines x2 and x3, although not shown graphically, are vertical asymptotes in example 6. So, in a similar way, the line YB, this is the horizontal line. This is the horizontal asymptote of the graph of y-axis. Is either this approach, they are not the same. This x approach is infinity of f(x) is b, or x approaches negative infinity, f(x) is b. Okay, and we will say finger 6. We can find finger 6. We know this is f(x) 1 over x minus 2. And when the vertical asymptote is x2. Here we want to find if this function has a horizontal asymptote. This means we will want to find the limit x approaches infinity or x approaches negative infinity. We find the limit x over minus 2, x 1 over x minus 2. We find the limit is equal to what? Here, limit, we will find this. We find the numerator, this is the constant 1, right? But here, the denominator gets larger and larger without bound. So we know 1 over number gets larger and larger without bound. We know this is approaching 0, right? Because, for example, give you this one, this last number. We find this approaching 0. Okay, so we find this is B, right? So this means we can find a horizontal vertical asymptote. Asymptote is y is B, B is 0. So we can find y is B is a horizontal asymptote in finger 6. And also we will find this one in finger 7. Finger 7, we find this is the x approaches infinity. We can also approach 0. This is also B. We can find out Y is B. It's a horizontal asymptote. Asymptote. Okay. Now, do you understand vertical asymptote and horizontal asymptote? Do you know how to find asymptotes? Any questions? Okay, we continue. And now, because we will learn many definitions, we will learn the continuity of fractions. Let me see, continuity. Okay, we will learn the continuity of fractions. In mathematics and science, we use the word continuous to describe a process that goes on without abrupt changes. In fact, our experience leads us to simulate this is an essential feature of many natural processes. Is this notion as it pertains to functions that we now want to make precise. Okay, in the 3 graphs in figure 1, only the 3rd graph exhibits continuity at C. In the first 2 graphs, either this does not exist or it exists but does not equal to FC. Only in the 3rd graph does we have here. From the graph, we know this curve is not continuous, right? Because it's not this goes on without abrupt changes. Here we find this abrupt changes, so it's not continuous. And we can find a limit x approaches C does not exist because we can find one side the limit x approaches C from right. Here. This means x like this approaches C. And now fx here, fx. So this limit, so we can find maybe if this number is A, so it's A, right? And then we consider x approaches C from the left. Okay, this means x like this approaches C. Okay, we have fx like this approaches this number. This number we write L1. Of course, L1 is not L, they're not the same. So one left hand limit is not equal to right hand limit. This means the limit does not exist. And the second graph, we can find this is not a continuous line, have a abrupt change. Although the limit, we know the limit exists, we can find the right and the left limit, they are equal. So, but we know the limit is this one. This one. X approaches C, fx limit. This means x approaches C, x approaches C. We can find fx approaches, so approaches this one, right? It's A. It's not equal to FC here. This is FC. They are not equal, right? So this means abrupt is goes on with abrupt change. Now discontinuous. And the last graph, we can say, okay, from the graph we know y is fx is goes on without abrupt changes. And we find this. Limit x approaches C, fx, we find x approaches C, approaches, limit is fc, right? So this means if this equality succeeds, we say fx is continuous at the point C. Okay, at the point C. So we have the definition of continuous. continuity. Continuity of functions. We have definition continuity at a point. Let f be defined on an open interval continuous C. For example, AB and C belongs AB. Okay, we say that f is continuous at C if if this limit is FC. We may find this definition to require three things. First, this limit must exist, right? And FC exists. That means C is in the domain of F. And the last one is this limit must be FC. Must be FC. If it's equal to another number L is not FC, like the second graph, is discontinuous. Okay, so if any one of these three fails, any one of, the f is discontinuous at C. And thus, the functions represented by the first and the second graph of figure 1 are discontinuous at C. They do appear, however, to be continuous at other points of their domains. Okay, so we must remember, if it's continuous at the point C, we have require three things. First, this exists. Second, exists. Third, is FC. Although we know the third equality contains the first and the second case, but to make sure we are clear, so we will say require three things. Okay, require three things. This is a definition of continuity at a point C. And we will learn continuity of familiar functions. Most of the functions that we will meet in this book are either continuous everywhere or continuous everywhere except a few points. In particular, theorem 1.3b implies the following results. We will know that the polynomial and the rational function are continuous. Our polynomial function is continuous at every real number C. Do you know why? Why? Why a polynomial function is continuous at every real number C? Why? You know why? Continuous, this means at every point C, fx is fc, right? This time. Polynomial function, we will write it like this. It's a polynomial, the power is n, okay? And we learned that limit x approaches C, we learned this P and C by substitution. I hope you remember this. By substitution, the limit is P and C. So, of course, continuous, right? And also, limit x approaches C, Px over Qx is equal to Pc by substituting Qc. And Qc is not 0, if it's not real. So we also have substitution. This means a rational function is continuous at every real number seen in its domain. That is everywhere except where its denominator is zero. So we know continuity of polynomial and rational fractions. Okay. And also, we learned some important functions. The absolute value function. How we memorize absolute value function. The definition of absolute value function is this one. X greater than 0 is x. X less than or equal to 0 is equal to absolute value functions is equal to x the definition of absolute value function. X greater than 0 is x. If x is less than 0, it's equal to what? Yeah, it's equal to no. If you write this is x, this your means this one is equal to this one, right? But they are wrong. It's equal to what? Yes, it's equal to minus x. Minus x, we know. Minus 2, we know this is equal to 2. Minus 2? Yes, 2. So here, this x is minus 2, it's negative. It's equal to minus, raise 1, right? So it's minus x. You should remember this one is always non-negative. Right? It's always non-negative. Okay? And we know x is less than 0. This is minus x. We know this is a polynomial. X greater than 0. This is x. It's another polynomial. No, polynomial function is continuous at every number, at every point. Thus, the absolute value of x is continuous at all numbers different from 0 by theorem A. But, x approaching 0 is also 0 is equal to absolute value of 0 is 0. So, the absolute value function is also continuous at 0. So the absolute value function is continuous everywhere. Okay, it's continuous everywhere. This is the graph, we know. Fx goes on without abrupt changes, right? Without abrupt change. So it's continuous everywhere. Okay. And also, this means to the standard function operations preserve continuity. Yes, according to the next theorem, we will learn the continuity under function operations. This means we have f and g are functions. K is a constant. N is positive integer. We have continuity and function operations. This means f and g are continuous at the point C. So are k times f, l plus g, l minus g, m times g, and over g. provided that GC is not zero. F power n of n third provided FC is greater than zero if n is even. So this continuity under function operations. Okay? And theorem D it tells us continuity of trigonometric functions. It means the sine, cosine functions are continuous at every real number c, and the function tan x, cotangx, sec x, cosec x are continuous at every real number c in their domains. Okay, most of the time we will match these functions. They are continuous everywhere or continuous everywhere except a few points. And we will also learn today the composite limit theorem. And there is another functional operation, is composition. We learned before how to decompose composition, right? Decompose it as two simpler functions. Now the decomposition, we have composite limit theorem. This means the inner here, the inner function. This is the inner function. X approaches C, this approaches L. And F is continuous at L. We have and we can write is equal to this means we have first calculate the limit gx. We know gx approaches L, so we can write is FL because F is continuous at L. Okay, this is how to find the composite limit. And for example, example 4. Pure right is continuous at each real number. First, think about it. Example 4. Just think about it. Maybe today we have learned many definitions, right? Because this is a basic knowledge, so we have no other method. How to. If I finish what? The PPT? Next class, and that was the first two subjects. Next maybe now I will center it. You can print. You can learn it before. 3, 4, 5. Okay. Example. Yeah. So this means we will like this one for our yeah. No, I know. For example, for okay. This is what? Don't know. Now this is a composition. HX. HX is a composition. When decompose it, we can write HX is equal to maybe Yeah. F(x) maybe you can use decompose. Decompose it, right? You can write h f(x) is square g(x) is h square minus 3x plus 6. And hx we can write is equal to f gx is equal to f is equal to, right? And decompose like this. And when the f(x) and gx, these two functions both are continuous. So we use decomposite limit theorem. X approaches C, f gx is equal to f limit x approaches C gx, right? And then, okay, then we write is f x approaches C gx. This polynomial, the continuous C square, right? Because f is continuous, this C is any number, any real number. Find the limit hx. This is equal to hc. So limit is equal to hc. So we know h is continuous every point. So we can find h is continuous at each real number. We just separate. Any question? No? No questions? Hello, students online. Any questions? For example 7, example 4, no questions. Okay, okay. Why only 2 students respond? Only 2. Always these 2 students.
Teacher,
Huh?
teacher, when are we going to have final exam?
Let me see which one. Oh, this girl. What are you saying? You're listening
When are we
or
going to?
playing?
I'm talking about the exam.
Talk about what?
The exam.
Exam. Exam for we? Huh? 20th week. 20th week, we have the examinations. This means our last class, we will have the examination. Yes, for example, if tomorrow is our last class and tomorrow we will have the examination. So the last class, we will have examination. Oh, this is the date. I don't know the date. I haven't set it. 20th week. Yeah, 20th week. Okay. Yes, today is 15th week. And check our last class. Last class. Our last class is on Thursday. Thursday night. Thursday night. This is also high, also big. 20. Yeah. Not December is no. Oh, not December. It's January. 1月20. This time, this one, right? This time night. Yeah, we have, yes, we are on vacation. So when should I learn?
Sure.
Yes. Yes.
But
we learn
January is the vacation. We're not studying in January.
Yes.
Okay.
Like this student. Exam, maybe you for you. Because at that time we tend to be I think it's not we because if anything we will Okay, now we just learn, we just learn, this is we learn the continuity at a point, and then we will learn continuity on an interval. This means continuity on an interval ought to mean continuity at each point of that interval. This means, for example, AB continuous on this interval. This means every point in this interval, every point fx is continuous. So this means continued on an interval. That's exactly what it does mean for, this is an open interval. Open interval. Open interval. Okay? Open interval. If we consider a closed interval, here we face a problem. It might be that f is not even defined to the left of A. You know, it's not defined. F maybe is not defined B to the left of A. For example, this occurs for fx is in this interval, y is square root of x. X is not defined to the left of 0, right? And strictly speaking, limit, we find the limit x approaches 0. This does not exist, right? Because the left-hand limit does not exist. Okay, we choose to get around this problem by calling f continuous on a closed interval if it's continuous at each point of AB. This means if it's continuous at on the open interval and we consider the x approaches A from right. We just consider this is a one right hand limit. This must be FA. And for B, we consider a left hand limit. The limit must be FB. And we summarize in a formal definition. For example, this one. Although this limit does not exist, we know x approaches 0 from right. This is equal to 0, right? So it's equal to f0. This means fx is the square root x is continuous on this closed interval. Okay, so we have the continuity on an interval. This means f is right continuous. We have right limit, right continuous. This means the right limit is FA, must be FA. It's A, B, A, B is not FA. So if AB is not FB, so it's not continuous. So right continuous, this must be FA. The left continuous, the left side limit must be FB. Okay, so we see f is continuous on an open interval. F is continuous at each point of that interval. Is continuous on the closed interval. F is continuous on AB, right continuous at A, left continuous at B. Okay, and now do you understand this? Continuous on an open interval is easy to understand. Now, continuous on a closed interval. This means it's continuous on AB, right continuous at A, left continuous at B. And what's the right continuous at A? This is the right hand limit is FA. The left hand limit is FB. This is left continuous FB. Okay. Okay, maybe example, maybe next time we will give you example, okay? And because I think today we have given you many definitions, right? Give many recommendations. You can review it after class, okay? Okay, maybe you can say bye-bye. Well, I don't know. I haven't received messages from the office. Maybe I'm also waiting. This is knowledge. Wait, 消息. What's the 消息? The English one? Knows. Maybe knows. And if I know, I will tell all of you. Bye bye. Bye bye.